So it's one thing to understand what lattice energy is. It's another thing to try to figure out how we could actually measure it. This is something experimental scientists have to deal with all the time. It's there. You know that there's a attractive force holding those ions together, and you'd like to calculate what that lattice energy is. However, how are you going to do it? What Born and Haber came up with, in essence, is said, let's figure out everything that goes into from mixing the chemicals to forming that lattice and subtract out everything except the lattice energy. If we know those values, and let's assume we do, after all, we can look up most of them in textbooks, then what remains must be lattice energy. So here we go. Let's just start with a chunk of some solid lithium. I've worked with it, I've seen it. It's a relatively soft, silvery substance that tends to oxidize at the drop of a hat. And there's a single atom of lithium. And we've got some gaseous fluorine. Now, if we're being real, we have to recognize that that is a diatomic, right? It likes to bond to itself, so it's going to look like that. You get them near each other, they are going to form some lithium fluoride. But let's think about it stepwise. We need to form the individual atoms. Now, lithium's a solid. We could go solid to liquid, liquid to gas, or if that was available, let's go directly by the sublimation energy. And there it is happening, solid to gaseous atoms, individual atoms, nice. And there's the sublimation energy. Whenever I do this, I say, where in God's earth would they get that energy from? But let's assume they have all that data and life is good. We're going to see that they have everything except the lattice energy. Well, let's do something similar with fluorine. In this case, we need atoms, so it's not ionizing, right, to F plus and F minus. It's already in a gas. The only thing it needs to do is separate. That term is called dissociating. And if we do it simply for half of a mole or half of a molecule, if you will, we'll end up with one of each, right? We'll end up with one of these lithium atoms and one chlorine atom. And now we're ready to go. So this dissociation energy is known, and it's at the appropriate scale here. We'd have a mole of these atoms, a mole of those atoms. Let's ionize them, right? Because after all, these do ionize. And in this case, lithium will lose its electron, fluorine will gain. So we should have the ionization energy for each. There's lithium forming a cation. Yep. And there's fluorine forming its anion. Brrr. And there's the ionization energy for each. Notice that forming the anion's exothermic, and forming the cation is endothermic. That kind of surprises me. I mean, isn't that what lithium wants to do? But those are the values that we get. Fine, let's move on. We're going to combine them now. They are in their ionic form. They will form an electrostatic attraction. And that electrostatic attraction is the lattice energy. We don't know that. Is there anything left for them to do? There they are coming together. That's going to be our lattice energy. We don't know what it is. We do know, however, the overall energy of the reaction. How do we do that? Well, that's what Born and Haber said they could do. They could just throw that thing into a calorimeter, let them rip, and calculate all of the energy that's generated when these things react. And if you've done calorimetry, it's pretty straightforward. So there's overall how much energy was liberated during that reaction. The only piece missing is lattice energy. So do the math, do the comparison, and that lattice energy is over 1,000 kilojoules per mole. This is the Born-Haber cycle for determining lattice energy.